we have three different kind of criterion. Two related to the strength and one related to the yield criterion. For the stress strain curves, we will have the peak strength and the residual strength. So all of the stress combination to show the failure peak stress, then you will have the peak strength criterion. For all of the stress combination to have the material attain to the residual strength, then you will have the residual strength criterion. The yield criterion is related to the plastic strength or the permanent strength. All of these criterion should be expressed in terms of effective stress form if the effective stress principle proposed by Karl Tazagi is applicable. Okay, so this still debatable for rock mechanics if the effective stress is applicable to rocks. Okay, but for the rock mass, fracture rock mass, it could be applicable. We have the general form to express the failure criterion like this. So we can express the peak strength or residual strength in terms of sigma 1. The peak strength or the residual strength of the rocks will be function of sigma 2 and sigma 3. This will be kind of stress combination. For more coolant failure criterion, we assume the shear stress will be function of the normal stress. So there is a very big assumption. That is, we assume the material is failed by the shear stress. This is not 100% true. And the other important assumption for the more coolant failure criterion, we always assume the failure is along a specific plane. So this will be the assumption for the more coolant failure criterion. As I tell you last week, the intermediate stress sigma 2 will not significantly influence the strength of the rocks. However, it will be influence significant for soil. Okay, you need to remember this. So usually we can express the peak strength of rocks in terms of sigma 3. This will be the more coolant failure criterion. If we think about this is equals to y and this is x, then you will have a linear equation. So this will be the slope and this will be the intercept. We can express the sigma 1 and the sigma 3 like this. We can express the normal stress and the shear stress at the certain plane where have an inclined angle to the horizontal equals to beta. If you can get this via Mohr circle, okay, via Hall method. In terms of equation, you can express the sigma n equals to this and tau equals to this. So the sigma n and tau will be function of beta, as I tell you. So the combination of normal stress and shear stress vary when the constant plane rotates. And all of the possible combination of the sigma n and tau will be occurred along a circle. So there will be the Mohr circle. If you insert the sigma n to here and insert tau to here and make a arrangement, make all of the sigma 1 to one side and other to another side and divide it, then you will have this equation. The sigma 1 will be function of beta. Of course, it will be function of C and phi. The sigma 1 will be function of sigma 3 and beta. That means if you have a different beta, then you will have a different failure criterion. You will have a different, if you have a different beta, then you will have a different peak actual stress. Okay? So, for this equation, you can understand. If we have a specific plane, like a beta, I showed you the beta equals to 45 degrees plus 5 divided by 2. If the assumption of Moore current failure criterion can be accepted, then we can put this angle to here, to this, to this, to this, and to this. Then this formula can be largely simplified like this. If you put this to here, then you can get the equation, simplified equation for this. You can further simplify this like this. So if this is y, this is x, then you will have the slope here, and this will be the intercept. Okay? So that means you can freely interchange the failure criterion from the sigma n tau space to sigma 3, sigma 1 space. Understand? They will be the same. 所以你可以很容易的把破坏准则，在土壤力学的时候，我们破坏准则都是用 sigma n 跟 tau 去表示它的。但是你其实可以非常容易的去做互换，把这个破坏准则从 sigma n 对 tau 转换成 sigma 3对 sigma 1。Okay? Do you know what I'm doing now? I'm trying to show you you can express this for Moore current failure criterion. If you accept the Moore current failure criterion, if you accept all of the assumption, you can express the Moore current failure criterion in terms of sigma 1 versus sigma 3. Understand? 知道我在干什么啊？ Okay. If we assume the tangent psi equals to Kp, then this angle psi will be the angle between the failure criterion, the failure envelope, in the sigma 3 and sigma 1 space to the horizontal plane. 所以，如果我刚才说斜率是这个嘛，对不对？ I already proved this on the whiteboard for you. If the c equals to 0, then the Kp will be this. Okay? This will be the slope. So the angle psi here will be tangent psi equals to Kp. Okay? 没有问题吧？这条直线跟水平的夹角，如果是 psi 的话，那 tangent psi 就会等于斜率。Okay? Tangent psi will be the slope. The interception will equals to this. What is the interception means? What is the interception means in sigma 3 and sigma 1 space? I don't need the whiteboard, sorry. What is the interception here means? 这个截距是什么意思 ？Please give me some response. 截距是 sigma 3等于0的时候的 sigma 1p。单压强度太好了，非常感谢。所以这一个 sigma c 这个 intercept 2c Kp 的开根号就等于 sigma c， 就等于单压强度。 Okay? Excellent. Then, what will be the tensile strength? 张力强度等于什么 What will be the tensile strength? The tensile strength will be the extension of this failure criterion until this straight line hit the horizontal axis. What does this green point means? This green point means when sigma 3 equals to 0, then the rocks will fail under, if the sigma 1 equals to 0, if the sigma 1 equals to 0, then you will have the minus value of the sigma 3. Sigma 1 should be always larger than sigma 3, right? Sigma 1永远要大过于 sigma 3. So when sigma 1 equals to 0, it means that uniaxial condition. 当 sigma 1等于0，不管 sigma 1等于0或 sigma 3等于0，只要其中有一个等于0，那就是单轴的条件。When sigma 1 equals to 0, then the sigma 3 will equal to this negative value. What does it mean? It means the rock will fail under tension. Can you get this? So this will be the tensile strength. 这个就是单轴直接拉张实验岩石破坏的时候的 sigma 3，它会是负值。sigma 1等于0 ，sigma 3是负的，所以还是 sigma 1大于 sigma 3。Okay? From the geometry, you don't need to care about too much. This is only related to the geometry. If you know the phi and c, you can derive the intercept here. This will equals to 2c cosine phi divided by 1 plus sine phi. Should I ask you to prove this for the whole set? Anyway, we can assume the T tensile strength equals to 0 for rocks. It means the failure criterion for rocks will like this. If you neglect the contribution from the tensile strength of rock, can we make this assumption? Of course, you can make this assumption because this is on safety side. You neglect the contribution from the tensile strength, so you were always on safe side. For conservative, you can make assumption like this, but usually this will be too conservative. This will be too conservative. For soil mechanics, we don't need to mention too much about this. Automatically, we will cut here. We will assume or we will treat the soil without any tensile strength. Okay? So if you apply a tension stress to the soil, it will break immediately. No tensile strength. For rocks, it will be difficult. You can try, can you tear off a rock using your two hands? You can try to pull them apart. It will be difficult, right? So we do have the tensile stress, tensile strength. For practical purpose, which we will not really get this data point or use this sigma t equals to this to get the tensile strength. Also, you can calculate this from the C and phi. Usually, we will not take this value because this value will not really close to the fact. Instead, we will doing the direct tensile test, or we were trying to use the Brazilian test, or we were trying to use the 4-point bending method to get the T0. Okay? When you get the T0, then you will draw a straight line equals to T0, and to intercept with the failure criterion, then this will be the complete failure envelope for rocks. Understand? We usually call it tension cutoff. Do you know cutoff? So this will be the tension cutoff. And this part will be the Moore-Coulomb failure criterion. We accept all of the assumption for Moore-Coulomb failure criterion. Then you can get this. Okay? Until now, it is okay for everybody. If you have any question, please don't hesitate. Just ask. 没有问题啊。The Moore-Coulomb failure criterion has been widely used, but for soil mechanics. But for rock mechanics, there are some reason we will not really use the Moore-Coulomb failure criterion as frequent as soil mechanics. I'm not trying to tell you we cannot use Moore-Coulomb failure criterion. Okay? But for some case, for engineering practice, we prefer to use other failure criterion, but not Moore-Coulomb failure criterion, because we don't really observe a major shear plane for many cases. It's not always true. Okay? This will be the big assumption for Moore-Coulomb failure criterion. And the other, the failure plane is not always have an inclined angle to the maximum principal stress equals to 45 degrees minus 5 divided by 2. 对岩石而言，它破坏的时候，我们看到的破坏包络破坏面，我们看到的破坏面，并不是每一次都跟最大主应力夹45度减2分之5。Okay? And the third reason, the failure envelope, usually the failure envelope is nonlinear. It's not a straight line. So that will be the reason why we are not use the Moore-Coulomb failure criterion so frequently for intact rock. Okay? For discontinuities, we still use the Moore-Coulomb failure criterion. Can you distinguish this? Okay? I hope you still remember the JRC-JCS model. The JRC-JCS model take all of the assumptions of the Moore-Coulomb failure criterion. You will have the specific failure plane because it will be the discontinuity, right? Specific failure plane. And the fail is caused by shear stress. So this will be the assumption for the Moore-Coulomb failure criterion. And the JRC-JCS model take the assumption, both. Okay, this will be something related to the soil mechanics, and I will not spend too many time to show you. You can prove the previous equation. Okay, this will be some steps to show you how to derive the previous equation. Okay, this will be the step. This will be the step how to prove the KP and the intercept. Okay. So, if you are work hard enough, you are trying to follow the derivation by yourself, which I showed you for the last 3 or 4 slides. This will be some questions from the national examination for the professional geotechnical engineering. This will be some material prepared by Professor Tian. I will explain the question. There is a rock. The failure criterion follow the Moore-Coulomb failure criterion. The cohesion equals to 20 MPa, and the friction angle equals to 40. And right now, the maximum principal stress equals to 100 MPa. The minimum principal stress equals to 15 MPa. Is this rock stable? Can you prove it? How to do it? How to do it? So, for the answer here, it will be quite easy. If you have an equation, and if you still remember the equation, then the sigma 1 can be expressed in terms of Kb and the cohesion, right? Then I give you the phi and c, so you can get the combination between sigma 1 and sigma 3, right? So you can calculate the sigma 1, this will be the failure envelope. So the maximum principal stress equals to 150. The peak strength of the rock equals to 150. How about the in situ state? The in situ state, the sigma 1 equals to 100. The rocks can subject to 150, and right now, the stress, the maximum principal stress equals to 100, so it's stable. Okay? 我可以背150公斤，我现在背了100公斤，我还可以，我不会被这个荷重压垮，对不对？ So the idea would be this. This will be the answer provided by Professor Tian. If I try to answer this question, I will draw the figure correctly. I will not use equation because I cannot remember equation under any any condition. I cannot remember equation. Please practice this by yourself during our short break. Okay? 我们休息10分钟，想一想这一题，如果是你自己要回答，你会怎么回答？如果是我一定用绘图法，因为我从来不记得方程式。Okay? Okay, to solve these 3 questions, you can use the equation shows in the slides. It will be very easy and very simple. You can quickly get the calculation. And when the pore pressure rises, what will be the pore pressure to make the rock broken or fail? And this question asks you what will be the effective normal stress and the effective shear stress at the failure plane. When you solve this question, you can use the Mohr circle and the failure envelope to solve this question. It will be more easier for you to understand the whole story. The question will be quick, but the equation will not give you some insight about the physical meaning. Okay? Please, you have a homework. You have already have a very long time. You don't really have any questions for the homework. So, please, and turn this homework to me next week. I will quickly go through the Griffiths crack theory. The Griffiths crack theory will be the foundation of fracture mechanics. The fracture mechanics will be a very important branch for mechanics. They dealing with the crack propagation. So in rock mechanics, there are some researchers working on the rock fracture, the crack propagation. Please do not worry about too much about the theory behind the Griffiths crack theory. I will highlight the most important information for you. So the basic idea, the Griffiths crack theory will use the energy instability concept to calculate analytically to calculate analytically about the crack evolution, the crack propagation. OK， 所以这个最主要就是利用这个所谓的就是这个能量不稳定法去计算，就是以这个解析的方式去计算裂隙的 propagation。如果你要一个裂缝，这个裂缝受到应力了以后，它会怎么样子 propagation？The idea will be like this: if you have a crack, and you can calculate how the crack propagate, continuously propagate. So if the stress at the crack tips goes above this value, then it will be start to propagate. So you can calculate, if I give you the stress state like this, and you can calculate what kind of combination of stress will make the crack propagate. So you can well use this to derive the failure criterion. Okay, the combination of sigma 3 and sigma 1 to make the crack propagate. This will be the analytical solution for the Griff's crack theory. He will get the combination to make the crack of the rock propagate. So this will be the failure criterion. So you can find the failure criterion will have two parts. The first part will be this combination, and the other part will be this combination. That means the failure criterion have two functions. Below this threshold, you will use one curve to describe the failure criterion. Above this threshold, you will use another equation to describe the failure envelope. And the T0 will be the tensile strength of materials. Okay? If you accept this, then you can change the failure criterion in terms of the normal stress and shear stress. So before we're trying to show you how to convert the space from the normal stress, shear stress to the sigma 1 and sigma 3. Right now, of course, you can convert from sigma 1 and sigma 3 to the sigma n and tau. So the failure envelope will give you the same idea. Okay, so this will be the failure envelope derived by the Griff's theory. You can find a very important features for this failure criterion. The first, it's nonlinear. Okay? The second, it seems like give you a tension cutoff. Okay, so it's a kind of a perfect failure criterion. But actually, this failure criterion is not a very popular. Okay, it's not really a very popular failure criterion. However, the Griff's crack theory give a lot of insight to understand the mechanism of rock failure, especially for the crack propagation. Okay. So as I mentioned before, this Griff's energy instability concept already became the foundation of the fracture mechanics. And this theory can well explain the size effect, as I introduced you. If you have a larger sample, then the strength will reduce, because you will have more defects. If you have more defects, then it will be more easy to have the crack propagation and make the rock, make the brittle material fail. So this kind of concept is also oriented from the Griff's theory. Okay, I was trying to summarize a lot of testing condition for rock mechanics. If you have a failure envelope like this, the space, the horizontal axis will be the normal stress, and here will be the shear stress. You can find this. The failure envelope will not really a straight line, but the curves. Here shows you some more circle. Can you imagine what is the more circle for this? You know this will be sigma 3 and this will be sigma 1, right? Sigma 3 equals to 0. So it means this will be the uniaxial compression test. What will be the sigma 1? The sigma 1 will be the uniaxial compression strength. Okay? What is this? This more circle, sigma 1 equals to 0, and sigma 3 will be minus. Then the sigma 3 will be the tensile strength equals to sigma t. Okay? How about this? This will be the rock failed under triaxial condition. If we try to express this in terms of the sigma 3 versus sigma 1, you will have a failure envelope. Again, it's nonlinear, and it seems you have a so-called tension cutoff. Okay? What will be this point? This point will be sigma 3 equals to 0, and this will be the peak sigma 1. Then what will be this? What will be this? This will be the uniaxial compression strength. Okay? What will be this? Sigma 1 equals to 0. Sigma 3 will be minus. So this will be the tensile strength. Okay? What will be this? This will give you a sigma 3 and give you a peak sigma 1. So this will be the failure under triaxial condition. Again, you will find the failure envelope is not linear. Right? From here, you will find the failure, you will find the more circle when the rock failed. Here, you will have a single point without the true more circle. I just put the sigma 3 and sigma 1. There will be a single point. When you try to draw a more circle tangential to the failure envelope, then we will predefine the failure plane. You can get the failure plane. For this, we do not really guarantee any specified failure plane with any specified angle. We are not really know what will be the failure plane, the angle of the failure plane. We are not pretty sure. Unless you accept the assumption from the Moore-Coulomb failure criteria. Then you can determine it. Okay? For rock mechanics, we are not really pretty sure what will be the failure plane, the orientation of the failure plane. Because some of the combination of the stress state will not really make the rock fail under shear stress. 很多的应力条件，其实我们并没有办法保证岩石是因为剪力造成的破坏，它并不是剪力破坏。OK， 比如说这里，它的破坏其实是张力破坏。单轴压缩实验，很多的玻璃面其实是垂直的。You will have the failure plane. You will have some micro cracks parallel to the maximum principal stress, but not have an inclined angle. Okay, so it's not really failed by shear stress. For more Coulomb failure criterion, they pre-assume the material is failed via shear stress. 摩尔库伦破坏准则里头有一个先决条件，就是假设材料是简易破坏，岩石不是，岩石不是全部都是。Okay, this will be the plot drawn by myself. I drew this plot already almost 30 years ago. Almost. Why I draw this? I started my PhD program. During that time, I tried to take the national professional geotechnical engineering tests. So I tried to prepare some materials. 我在念博士班的时候要考那个技师考大地技师，所以我就自己整理了一些东西。Okay, I adding one more circle more here. Is there somebody know what is the stress condition for this more circle? We will have the direct tension test here. We will have the uniaxial compression test here. Here will be the more circle of Brazilian test. If you still remember, sorry, it's too small. If you still remember, we will have 3 times the absolute value for the 3 times for the sigma r, the ratio between the sigma r and sigma sigma. So one will be the maximal principal stress, the other will be the minimum principal stress. One is positive, the other is negative. Are you still remember this? I don't remember which one will be sigma r and which one will be sigma theta. Okay, this will be sigma theta. And this will be sigma r. This will be positive and this will be negative. This will be 3 times larger than this. If this is -1, then this will be 3. Okay? So you can imagine the Mohs circle will be like this. The distance from here to here will be 3 times larger than the distance between here and here. Okay? So you can try to use the direction tension uniaxial tension test to derive the sigma t. You can use the Brazilian test to get the sigma t, and you can use the 4-point method to get the sigma t. Okay? So usually the different testing method, you will roughly get the different testing results. For example, if we treat the directly tension test will be the best testing method if we assume this. Okay? Then the Brazilian test will get the results 1 to 10 times larger than this. And the bending test will have 2 to 3 times larger than this. Another useful place for the Grief theory I mentioned to you before. The Grief theory can well explain why these 3 different types of testing results yield different testing methods yield different testing results. Okay, I'm not trying to tell you this is the most convincing testing result. I just showed you different testing methods yield a little bit different testing results. Okay, and there are some empirical failure criteria. this will be the one of the famous nonlinear failure criterion of rock, which is proposed by Beniowski. I think maybe you're already familiar with Beniowski because of the RMR, rock mass classification system. Okay, so he provided you two equations. One in terms of sigma 1 versus sigma 3. The other in terms of tau versus sigma n. Okay, you already know they can convert each other easily. Okay, then you will have some parameters here, A, sigma c, and k. The sigma c will be very easy to obtain. You have several approaches to get the sigma c. You can use uniaxial compression test to get the sigma c. You can use the point load test to get the sigma c. You can use the Schmider hammer to get the sigma c, right? And actually, you can try to use your hammer, knife, and your finger to get the sigma c. Roughly qualitatively. I give you a table, right? You can use your hammer to get the sigma c roughly. So sigma c is not really a big deal, but sigma c is very important. But it is easy to obtain. For rock mechanics, sigma c will be the most important parameters. One of the most important parameters. Okay? And Beniowski gave you some guidelines about A and B here. So the A, for different lithology, you will have a different A. For different lithology, you will have a different B. Okay? So A is for this equation, B is for this equation. For K and C is not really relevant to the rock type in general. The K is roughly equals to 0.75 and C equals to 0.9. It's not really highly related to the lithology. Okay, so if you have an A, if you have a K, and if you have a sigma C, then you will have the failure envelope. Okay? How to get a failure envelope of soil? Basically, you were trying to use the directional test, or you were trying to use the triaxial test to get the C and phi. Of course, right now, everybody trying to use the SPDM value to get the C and phi. Anyway, it's not good. It's not very good. Anyway, for rock mechanics, usually we were trying to use this kind of empirical equation to get C and phi because it's not as frequent as soil mechanics to use the triaxial test because of it's a little bit more expensive than soil mechanics test for triaxial test. But we should not only rely on this kind of empirical equation. Sometimes the laboratory test is still essential, especially for large engineering projects. Okay? You already learned this several weeks ago. I tell you the Hoek and Brown failure criterion will be the most commonly used failure criterion for rock mechanics. Okay? So the Hoek and Brown failure criterion will be expressed in terms of sigma 1 and sigma 3. So this will be sigma 1, sigma 3, and you have some parameter. The most important parameter will be sigma c, okay, which shows you the uniaxial compression strength. And you will have the M and S. The S will be a parameter highly related to the microfracture exists in the rock, in the rocks. If you have a lot of fractures, then the S will almost approach to 0. If you have intact rock, no microfracture, then the S will approach to 1. Okay? If you carefully examine this equation, if you carefully examine this equation, you will find the S is highly related to the intercept of the failure envelope. If you have S equals to 0, it means you will have no intercept in the vertical axis. Understand? If we talking about the cohesion, it means it's not really directly related to the cohesion. However, it's indirectly related. If the S equals to 0, then it means the cohesion of the rock mass equals to 0. Okay? If you have a lot of microfracture and S equals to 0, no cohesion. If S equals to 1, no microcrack, then you will have a larger cohesion. Can you accept this kind of philosophy? 可不可以接受这样的逻辑？如果要是有一大堆的微裂隙，然后 S 等于0，它的概念就几乎就是破坏暴露线没有凝聚力，它只能靠摩擦力来提供强度，有道理吗？哈。可是随着你的 S 增加，从0增加到1，你的 cohesion 就会越来越大。OK， 如果 S 等于1，它的 cohesion 就是刚才我们推导的那个 cohesion。刚才前面推导就是它的那个 cohesion 跟 sigma c 有一个交换，有一个互换公式嘛，对不对 ？OK， and this parameter m is highly related to the lithology. For example, carbonate rocks, the m equals to 7, and the argillarious rocks, the m equals to 10. So if you have a m, if you have a s, then you will have the failure envelope. Okay, this will be the other rock types. You will have different m. This will be the famous testing data documented by Hoek and Brown. Every single point here will be a testing result. So how many testing results you have here? I think roughly more than 100. So what is this? All of this data point will be the uniaxial compression test. OK， 所有的资料点在这里，通通都是单轴压缩实验。Why? Because sigma 3 equals to 0. What is the data point there? It will be the uniaxial compression strength. 在那上面的任何一个点就是单压强度。那你所有的岩石去压，不会每一颗岩石都压出一模一样的单压强度吧？对不对？所以它有一个 variability here. So the uniaxial compression strength varied in this range. The other will be the testing results of the triaxial test. So you will have many triaxial tests. In general, you will find the failure envelope is not really a straight line. Instead, it will be a curve. If you make the regression and get the equation, the R square will equal to 0.87. It's not too bad. According to this, Hoek and Brown, they test a lot of different rocks. They find the shape of this curve is highly related to the lithology. So we test a lot of different lithology. Then the M controls these curves, the shape of this curve. So he can determine the M. 因为不同的岩石，你会得到不一样的形状，那个形状会被 M 控制 ，M 会调整它的那个破坏暴露线的形状，所以他就去归纳，做了不同的岩石，做了不同的实验，有不同的形状，不同的形状就有不同的 M 值，所以他就归纳出了一些这个实验的结果。This is for granite. I think the result is quite nice. Okay, the regression results is quite nice. So, different rocks, different lithology, you will have different M. For rock mass, I also shows you here, this will be the failure envelope of rock mass, including discontinuities. The MV will be function of the lithology and the GSI as well. I hope you still remember what is GSI. GSI is the geological strength index. This will be a value from 0 to 1. From 0 to 100. And this value is determined by the rock mass structure in the vertical axis and discontinuity condition in horizontal axis. From the worst, from the best here 100 to the worst 0, 0到100, you can determine the GSI. So the MB and S will be function of GSI. Here, which shows you here. The MB will be function of the lithology and GSI. The S will be function of GSI. So you can determine the failure envelope of rock mass easily. Okay? I told you I will give you this, right? Maybe I will ask you to get the failure envelope from the Hoek Brown failure criteria. It could be. Understand? 刚才那个问题，我说不定不直接给你 C 跟 5， 我不要用摩尔库伦破坏准则，我说不定给你这个 Hoek Brown 破坏准则，然后给你 GSI， 我给你这个 M， 我给你盐性，叫你去求它的破坏暴露线。Could be. So this will be the table to show how to derive the GSI. Okay, I will stop here.